I got multiple tripods.
Gorgeous.
Are you good?
Yep.
Are you playing?
Yep.
Okay, so I have two penguins, OG and little g. Pretend they're charges. We can find the electric force between them, KQQ over R squared. If I take one charge away, there's no more exact force. We don't know the force. But in this empty space, we can find the force field in newtons per coulomb. Right? Excuse my hair today. But in this place, we have an electric field that's newtons per coulomb. It's the newtons of force per coulomb of thing I put there. If I put more coulombs, I get a bigger force, right? Okay, so now let's look at that with energy instead of force. If I take this tube, this is positive and this is negative, and they love each other, they're attracted, and I do some work. That work is now stored in these two charges and the distance between them as electric potential energy. This is the important part, Alan. If I take this charge away in this empty space here, you can't really calculate the potential energy, can you? Because you don't know what the other charge is. But you can get the energy per coulomb of thing I put here. Make sense? It's kind of like force and field, except it's energy and potential. So it's not electrical potential energy, it's just electrical potential. What's the unit of energy? Joules. What do you think is the unit of potential? Joules per coulomb. Very good, very good. Okay, so we're gonna learn about those things. Oh. So you have electric potential energy, you got all this stuff, I think, moves towards you, and I'll share these slides with you. You can have a uniform field or you can have a non-uniform field. If you have a point charge and you move out from the charge, what happens to the energy as you go out there? Your potential energy is going to increase, right? It's a non-uniform field, so it's getting bigger as you go out. I should mention with the force, what's the formula for force, electric force? Good, KQQ over R squared, yes? Energy is KQQ over R. It's a little different. Energy is always easier. And we got a lot of E's with electricity, so we say EP for energy. We go KQQ over R. Notice it's just like gravitational potential energy. It's GMM over R. With electricity, it's KQQ over R. What's the difference between this formula and the force formula?
Use R.
R, force is R what? Squared, right? So there's no square here. So with force, if I double the distance, I get 1/4 of the force, right? With energy, if I double the distance, what happens to? You get half, yeah. Well, actually with potential, you get twice. You get double. Because this is negative, right? So remember with EP with gravity, we had negative GMM over R. You remember that? Okay. Why is it negative? Why did we make it negative? It's confusing. Daniel, remember? It was a puzzle, right? We had to come up with a mathematical story that when you increase the distance, you increase the potential energy. But when you get really far away, it has to be what? 0. The only way to do that mathematically is for it to be negative. You'll notice there's no negative in the electric, bless you, in the electric potential energy formula. There's no negative. Why not?
Because it's getting bigger when
It is getting bigger when it gets farther away. And it also is goes out to 0. It's the same situation. That has to be negative if it's attractive. The difference between electricity is it can be attractive or repulsive, right? What two charges make attraction? Alan? Plus and minus. Positive and negative. If you have a positive and negative here, this answer is going to be negative. So we don't need it in the formula. But it is negative if it's attractive. What if it's positive and positive charge? Then it's repulsion. So your potential energy is actually positive. Because if you let it go, it's not coming back, it's going the other way, right? So it will start off positive and go down to 0. Sorry, I'm giving away all the secrets here. This is the formula for electric potential energy in a non-uniform field. And we talked about the similarities already, so I'm going to move on then from there. Try this on a scrap of paper somewhere. Okay. This says from a long way away. What does that mean? It's going to be 0, right? So
You just use the 1 meter.
yeah, exactly. You find out the energy, and that's going to be the same as the amount of work that you need to do. Do you have to do work to bring these two charges closer together?
Yes,
Yes. Why do we have to do work?
we have same charges.
Yeah, they have the same charges. They're repulsive, right? So instead of stretching a spring, it's like squishing a spring together. Is this 0.216? What would be my unit for this? Joules. Is that right? Did I do that correctly? So just a pretty simple calculation, right? KQQ over R will tell you the energy. If I want to squish those two charges to within 1 meter, I'm going to have to do this much work. If I release them, what's going to happen? They're going to shoot apart, right? What's going to happen to the kinetic energy as they get further and further apart? It's going to decrease. It's going to decrease. And eventually there will be no push there at all. Yes.
But if we're holding them from a long way away, it means that there's no more energy.
Yeah, if you're holding them from a long way away, they're not doing
So
anything.
if we release them, will they still go?
No, but I should point out that this does not exist in our universe. It's this, what we really say when we say a long way away is we mean an infinite way away, which we don't really have. So it's a theoretical thing. Again, it's like a story we made up, you know, to try and explain it. The truth is, there's no distance in our universe that two charges will not interact with each other. But if you're an engineer, then you don't really care. You just want to know in general what happens, you know. So, a couple of things to think about. Energy is a scalar. So you guys just did a quiz, right? And you added up electric fields. You have to think of direction. You have to add the vectors together. Energy is not like that. It's very nice. You don't have to worry about direction. There is no direction. So you do not have to do vector addition. So if you're not doing vector addition, then how do you add them up? You just add them up. That's it. Just add the numbers. Energy has no direction, but it can be positive or negative. What does that mean, if not direction? Jack, say that again. Ah, yeah, kind of like O's energy, yeah. Kiana, what were you gonna say? Say that again. Yeah, I think that's a good way to put it. If you push something up a hill, that takes energy from you, right? So that's like it's like a loss of energy almost. It takes energy from you. If you want to get something down the hill, you just let it go, right? So it kind of takes negative work to do it, because you don't have to do anything, and actually you get the energy. It's not for free really, but you know. Okay. So if you're gonna squish two positive charges together, that takes energy, so therefore the work is positive. Okay, try this.
What is UC?
Micro times 10 to the negative 6.
Why did you square the bottom?
Oh, shoot, thank you.
That's a Google.
That's force. Good job, Parham. Let's give Parham a golf clap. Yay. I did that on purpose. Just to see.
Is it 6.93 to the power of 11?
Does that sound right? Let me do it quickly on the cover. I was going to do it in my head, but. -6 times times 5 times 10 negative 6 equals divided by 0.5.
No, it's wrong.
First of all, it's negative because this charge is negative, so you can't ignore that. It makes a difference. So your answer is negative. I got 0.63 or so. Now that's weird, right? Yeah.
That's the amount of energy pulled apart, right? Is that what that
That would be the amount of energy to pull these two apart, but they're attracting, right? So to bring them closer together, is that gonna take work? No, you just let it go, right? So it's kind of like the opposite of doing work. You're getting energy out of it. The potential energy is already there. So somebody way back in the day, God maybe or whatever, she like grabbed it and stretched it all apart, right? Long way away, and then you let it go, and it just does it. All that potential energy has turned into this. So we get our change in potential energy is negative. So instead of having to do work, we kind of, it's like we already saved up somehow. It's like a trust fund, you know? I'm waiting for my rich uncle to show up and tell me, no, trust fund, this guy. Okay. So in this case, bringing this negative charge near a positive charge, it generates energy and therefore your work is negative. So turn to the person beside you, around you, 2s or 3s or whatever, and tell each other how work can be positive and how work can be negative. How can work be positive and work be negative?
I don't.
Oh, I was like looking for my phone. That's it for this.
That's why I want